separatrices.
All right. You've seen some dynamical models at the symposium. I wanted to count exactly how many. So I asked ChatGPT. Turns out of the 103 abstracts, 34 of them use RNNs or dynamical models. 22 of those are trained, and 8 of those are trained on neural data. Disclaimer, I did 2 iterations, and then I asked, be more cautious. They may mention dynamics, but not actually use a dynamical model. So I had to, and that reduced these by about half. So, okay. You have a dynamical system. You might have a phase portrait that looks something like this. You have fixed points, and you have this thing, which is a separatrix. What is this? Well, if you have this Bazin, which is the Bazin of attraction of this fixed point here, and you have this Bazin of attraction, which is for the fixed point here, the separatrix is the one that divides these two. Why is this a useful thing to know? Well, let's say this is your choice axis, which is whether you decide A or B. And this is the input direction. Let's say you have an input that moves you across from one Bazin to another. And maybe there's some sort of an optimal direction which can move you to the separatrix and change your decision in the easiest way. So these are some, if you're interested in decision making, maybe you want to know these. So we were inspired by work on fixed points, which happened about 12 years ago by David Cicillo and Omri Barak, which is they had the idea, and Omri Barak is my supervisor, so this was convenient. The idea is that you have this scalar function which can help you find these fixed points, because the minima of this scalar function of this, which is just the norm of the dynamics, are exactly these fixed points. So if you run gradient descent, then you get a numerical method to find them in high dimensions, like recurrent neural networks. So we had the idea, can we do the same with separatrices? So can we find a function that's sort of smooth and so on and minimized at the separatrix? All right, how do we find such a function? So let's say you have this bistable, I call it the sandwich of bistability in high dimensions. So you have an attractor here, attractor, and then a separatrix in between. What we do is we think of, we only want to map the bistable axis. And so we can map it to a canonical sandwich of bistability, which is in one dimension. And you might have an equation that looks something like this. So psi minus psi cubed. And so you have an attractor at -1 and at 1, and then a separatrix, which is just a point at 0. And what we want to do is map our high-dimensional system from here to a value point on this 1D line. And we will end up doing this with a feed-forward neural network. And importantly and crucially, this is the main takeaway. We want to map the attractors to 1 and -1, and the separatrix to 0. And that's exactly what we're looking for in the scalar function. And now is a little bit of math. Bear with me. What we want is, as x evolves according to our dynamics of interest, that psi of x evolves according to this 1D system. How do we put these together? Well, this looks like a big equation, but it's exactly this equation that I've written again, just adding explicitly the dependence on x. With a few more steps, we can transform it into a PDE and turn that into a loss function for a neural network to optimize. Where is the Koopman operator? That was in my title. Well, it's actually right here. Turns out it's a cousin of the Koopman operator. It's also called a Lie derivative. But if we write this equation in a Koopman in an operator sort of notation, it looks a lot cleaner, and it actually starts to look a lot like a Koopman like a Koopman eigenfunction. And we were wondering what's the relation between these two, and actually there's quite a nice one. So while this system gives you this behavior, which is this 1D bistable behavior, this system gives you a linear system which takes the attractors to infinity and minus infinity instead of -1 and 1. And so if we want to transform a solution of a Koopman eigenfunction into one of these guys, all we have to do is map the infinity to 1 and map the minus infinity to -1. And this effect is basically squashing. It's sort of squashing the infinities to ones. And that's why we call this squashed Koopman eigenfunction. All right, now for some results. We show that it sort of works in 1D. Here's a 1D bistable system, and we sort of capture the separatrix at the 0 of our function. We can do this in 2D, and you have sort of a funny S-shaped separatrix here, and we are able to capture it. You can capture it in a trained recurrent neural network, again in 2D. It's trained on a 1-bit flip-flop, and so you get bistable dynamics, and indeed, we're able to capture this separatrix. You can also do this when there's no fixed points. So here's 3 limit cycles. 2 of them are stable, and 1 of them is unstable, and we're able to capture it with our method. All right, so I've shown you that it works in 1 dimension, and I've shown you that it works in 2 dimensions. Obviously, the next step is 668 dimensions. Here's a data-trained RNN. We didn't train it. It was from people, the folks at Genedia. They trained a mouse to make some decisions, and then trained an RNN to the data, to the neural activity of the mouse. And we analyze it. We just downloaded this RNN and analyzed it. The trouble with 668 dimensions is visualizing a separatrix. This is a n-1 dimensional manifold in n dimensions. Here's the 2 attractors. What we did is to join them with polynomials, basically, continuous line, and to find out as you walk along this line, where do you hit the separatrix? Where do you transition from one Bayesian to another? And we use this, and then the next thing we can do is along those same curves to evaluate our Koopman eigenfunction, which we've trained on this system. And we can see that here's 3 different curves that I'm showing you, and that the zeros of these curves align well with the true separatrix points shown by the vertical lines. And finally, we can compare these for all of these curves and see that there's actually a pretty good match. The next thing that we want to do is, going back to this picture that I showed you at the beginning, is to find this optimal direction, because now we can use our scalar function for this. So let's say you could deliver an instantaneous pulse to the neurons of your choice, let's say using optogenetic holographic stimulation. Let's call this perturbation delta. So what you want to do is the following constrained optimization. You want to minimize the norm of the perturbation delta subject to the constraint that the final point is on the separatrix. And that's given by making our Koopman eigenfunction 0. And we can use this idea, and here's the numerical result. I'm showing you the norms of several points. The first is the norm of this optimal direction that we found on this large RNN. Here's the point that you would have got if you went straight towards the target fixed point. And so it's a little bit further away. And here's if you were going towards random points on the separatrix. So we indeed find that we get one that's with much smaller norm. All right, to summarize, we propose a framework to find separatrices in high-dimensional nonlinear dynamical systems. How we map the system to a canonical 1D system. And we demonstrate this method on a variety of systems, including data-trained RNNs. And finally, we use it to design optimal perturbations. Along the way, we understood a little bit about Koopman operator theory, but that's more for ourselves at this point. All right, thanks so much. If you want to try it out, please let me know, because I'm excited to sort of, apply it to new systems. So yeah, and we have a NeurIPS.
Thank you.